Hello. Last video we looked at cyclotrons, which are a particle accelerator. Now we're going to look at another type of particle accelerator. Now we're going to look at the big boys. And these are the huge particle accelerators. The first one we'll look at is called Fermilab. And it is a particle accelerator that has a circumference of 4 miles. And it was once the world's highest energy particle accelerator. So particle accelerators, research ones, are ranked according to how much energy the particles have, because basically the particles are collided together, and what you see is dependent on how much energy you put in. It's like if you're colliding two cars together, if they just bump each other at 5 kilometers an hour, not much would fall off. And if you're only learning about what makes a car from bits that fall off, that's no good. So you then collide it at 20 kilometers an hour, some more bits fall off. You do it again at 60, you do it again at 100, do it at 150 k's, and eventually all the bits that make up a car will fall off and you'll be able to identify them. And so that's sort of how particle accelerators work. They might take protons and protons and collide them together and see what comes out, and you find out all the bits and pieces that make up these particles. And so unfortunately Fermilab is shut now. However, it had some major findings. It found what was called the top quark, which is one of the subatomic particles that go to make up protons and neutrons. And it was a host of a whole lot of experiments, including a lot of neutrino experiments. But it's now, what did it look like? That's it there. There's its characteristic building. There's a linear accelerator, and then it has two loops that are effectively underground, and then there's water around them for cooling and stuff. But basically it's been shut down now because it's been superseded by the next one I'll talk about. But there's more diagrams. So this is just an overlay, and what they were getting up to is 1.96 tera electron volts. Remembering that electron volts are a measure of energy, so you could convert this into joules, but of course we're dealing with atomic physics. It's quite more convenient to just leave it in electron volts. Now I forgot to say that this was near Chicago in the US. Okay, so it's been wound down, closed down in 2011/12. There was a bit of a fight to keep it going, but there just wasn't any funding available for it. And so it used to send a proton around in one direction and an antiproton in the other direction. Now what's this got to do with electric fields? Well, these particles were contained inside a vacuum tube, and it was the magnetic field that controlled their path through that tube. And so there's a whole massive amounts of magnetic fields being generated and controlled, all in this hub, to make these particles actually go round, get accelerated, and then collide with each other. Pretty high powered stuff. And these are the vessels in which the collisions occurred, so they were full of sensors that would track the particles. And that's what one of the sensors looked like, and there's a human being to show the size. Lots of sensors, lots of electronics, lots of cooling, lots of engineering basically, and so massive amounts of engineering and physics involved in it. Now CERN is the one that replaced it, and it is now the largest and particle accelerator available. And it's gone through a number of transitions, but now it's called either CERN or what's called the Large Hadron Collider. And you can read all that. Founded in 1954, is credited with the place that the basically the internet started, or the idea of the internet started, because people wanted to share information between scientists. Physicists wanted to share information, and there was no easy way of doing it. And so this is it. It's located in Europe, and when you watch one of the videos, I'll put it on the OneNote, you'll get a much better description than I can possibly give. But this is the loop, the major loop, and you can see it's quite massive. And then there's smaller loops as well, and it's all underground. It's about 200 feet or 200 meters underground to protect it from stuff. It uses enough power to actually power all these houses, plus those about 10 times over. It uses a massive amount of power. When they turn this thing on fully and they run it, they have to let all the nuclear reactors and the power stations around Europe know that they're going to suck this energy out, because it just uses so much power. It's a collaboration between a whole lot of countries, and so it's an international research procedure. And some of you have probably looked at this in your research assignment as well, and so you probably know a bit more about it. Basically, it has loops, has the Atlas and the Alice are the main collision centers, but there's some minor ones as well, and the LHCb, and so there's a whole lot of experiments that relate to it. And these are the loops that happen, and this is sort of following the path of protons. They start produced in one area, then they go round, they get to 0.3 the speed of light, then they go around here and they get to 0.87 the speed of light, then they go into here, and then they get into here and they get up to 0.999999 the speed of light. So they're getting accelerated faster and faster, and they need to have massive amounts of energy to cause that acceleration, because it's not a simple matter. Once they get to this speed, the particles themselves become massive. They actually gain mass. It's part of relativity that relates to relativistic mass. And so I'm going to pop these videos on the OneNote. They can explain a lot better about it than I can. Alright, but it's fairly interesting. Now, if you want to crank it down a little bit between a cyclotron and something like the LHC, you might go for a synchrotron. And the synchrotron is being built near Monash University in Melbourne, and it's being used to accelerate electrons around, and so you can then do a whole lot of experiments with the beams to look at things. And basically it's an electron accelerator made to go round in a circular ring by magnetic fields and used to produce X-rays. And so there's a whole lot of science in it. If you're a Victorian student, you're made to know everything about it possible. So you can pause this and have a read of it, or you can go onto the internet and have a look. It's fairly interesting, but relatively small scale in the scale of physics experiments out there. Now, I just wanted to show you some contrasts of design. This is a synchrotron in France. This is the design for it. Bit of architectural, bit flashy, doesn't look too bad. This is an old one in America, but still quite elegant, with the grasses and design about it. What does the Australian one look like? Looks like this. A big shed with a car park around it. I wish they could have done a little bit more about their design. But anyway. So in the next video I'll start looking at some other applications, and I think there'll be 2 videos just looking quickly at some other applications of magnetic fields. Alright, bye.